Hello viewers, I Dr. Mala Sharma welcome you to my video number 135 of my channel MALACHEMPHILIC. 135 video is the 74th episode of Chemical Thermodynamics where the topic is multi-component phase equilibrium, freezing point depression. So let's start. Now, what is freezing point? Freezing point, that is the temperature at which the liquid and solid phase of the substance remains in equilibrium. So, liquid phase and solid phase, they are in equilibrium at the freezing point. And so, it is the temperature at which the liquid and solid phase have the same vapor pressure. Right? And we know in my earlier videos, we have seen that vapor pressure of the pure liquid lowered down by the addition of little amount of non-volatile solute. So, solid liquid equilibrium occurs at lower temperature. Okay. For that matter, what happened? Freezing point of the solvent will be lowered down due to addition of non-volatile solute, which is known as the depression of freezing point due to addition of non-volatile solute. Now, see here, this line, this indicate this solid liquid equilibrium. And this is the pure solvent and this is the solution. Now this pure solvent, here it is touching this equilibrium line. So here this is the freezing point of the pure solvent. Okay, but say this temperature is TF. So this is the freezing point, this temperature is say TF. But this solution curve at this temperature, it is not touching this equilibrium line. It is touching this equilibrium line where the solid liquid will be in equilibrium. That is at lower temperature. Say this temperature is T. So TF is the freezing point of the pure solvent and T is the freezing point of the solution, that is after addition of non-volatile solute. And this difference of this freezing point, that is T minus TF, that is delta TF, that is the depression of freezing point due to addition of non-volatile solute. Now, this curve is the plot of chemical potential versus temperature. Now, this line indicates for the pure liquid and dotted line for this solution after addition of little amount of non-volatile solute, right? Now, and this is the curve for solid. That means here you look at this curve. This indicates this equilibrium. Now, look at here. This liquid line, it is touching this solid line at this point. That means here liquid and solid phase are in equilibrium and that is the freezing point of that liquid, that is pure liquid, whose temperature is TF. Okay. But at this temperature, this solution line is not touching this solid line, this equilibrium line, it is not touching. Okay. So it is touching here at lower temperature T. So here this solid is there and this solution is there and this is their touching point. That means they are at equilibrium, which is at still lower temperature T. Okay. Yeah. Now here we have plotted the chemical potential of the solvent against the temperature. So as I told you, TF is the freezing point of the pure solvent, and at freezing point of the pure solvent we know that at equilibrium, okay, freezing point means liquid and solid are at equilibrium. At equilibrium, this chemical potential of the substance in different phases, here it is solid phase and liquid phase, should be same. So A indicates the solvent. So chemical potential of the solvent in the liquid phase must be equal to the chemical potential of the solvent in the solid phase. Okay. Mu A, chemical potential of the pure solvent. Now, when a little amount of non-volatile solute is added, then it becomes solution, and for this solution, see, mu A liquid phase, that is chemical potential of the solvent in the liquid phase, and this chemical potential of the solvent at the solid phase, that equilibrium, that means they are equal means they are in equilibrium. Liquid and solid are in equilibrium. That's why chemical potentials are equal. That occurs at lower temperature T. Okay. So at this temperature, T temperature, which is less than TF, this chemical potential of the liquid phase and solid phase become equal for the pure solvent. Okay. And therefore, T is the freezing point of the solution. Okay. And this C, T is less than TF. That means this freezing point of the solution or freezing point of the solvent after addition of little amount of non-volatile solute, that is less than that of the freezing point of the pure solvent, okay, or pure liquid. Okay. And delta TF, already I told you the difference in the freezing point. So delta TF is known as the depression of freezing point. Now, in the liquid solution, okay, that means I'm considering the solution. In the solution, this chemical potential of the solvent A, we can write by this equation, chemical potential in the liquid phase at standard state plus RT ln activity of A. But in the solid phase of the solvent, when only the solvent is present, that means pure solvent or pure liquid, then chemical potential in the solid phase, that will be for the pure solid. So that is mu star A in the solid phase. Okay. Then at equilibrium, these two are same. That means this is equal to this. So mu A star liquid plus RT ln activity of A is equal to mu A star solid. This is for standard state. Okay, standard state for the liquid phase, standard state mu at the standard state for the solid phase. Now, so RT ln activity of A, that will be, I have taken this side. So mu A star solid minus mu A star liquid. So RT ln activity of A. Now here, look at here then. Now here you see, we know that chemical potential of the pure substance, chemical potential of the pure substance means pure, how do you write, chemical potential of the 1 mole of pure substance, that is equal to, we know that molar Gibbs free energy. Molar Gibbs free energy. Okay. So chemical potential of 1 mole of the pure substance, that is molar Gibbs free energy. So here we can write G, that is molar Gibbs free energy in the solid phase minus molar Gibbs free energy in the liquid phase. So RT ln activity of A. So this will be equal to, this is the change of free energy during fusion. Fusion means conversion from solid to liquid. In that case, G liquid minus G solid. That means the free energy in the liquid phase minus free energy in the solid phase. Okay. But here it is solid minus liquid. So it is minus delta Gm, that is molar Gibbs free energy change during fusion. Okay. Sure. Then ln activity of A will be equal to, just we have to divide by RT, this equation. So once again this equation is written. Now differentiating with respect to temperature at constant pressure. So it will be ddt of ln activity of A is equal to, now there are two terms. One is delta Gm, molar Gibbs free energy change of fusion, for fusion, and another term is 1 by T. R is constant. So minus 1 by R. Now if you differentiate first function, differentiation of the second, that is dou of delta Gm fusion by dou T at constant pressure, plus second function. Second function is delta Gm, molar Gibbs free energy change during fusion, okay, into this differentiation of the first. First is 1 by T. Differentiation of 1 by T will be, that is T to the power minus 1, then minus 1. So T to the power minus 2, that means 1 by T square, and minus will be there. So ddt of ln activity of A will be equal to minus 1 by R, then 1 by T. Now here in place of these things I can write delta Sm, that is molar entropy change during fusion. Okay, because why? Because we know that dg is equal to C. We know that dg is equal to V dP minus S dt, right? So if you differentiate this equation with respect to temperature at constant pressure, then what we will get? Then we will get dou G by dou T at constant pressure. This will be is equal to your constant pressure, means dP is equal to 0. That will be is equal to your minus S. Okay. So therefore what we can write? That is dou of delta Gm by dou T at constant pressure, that will be is equal to minus delta Sm. And this is for this fusion. Okay. So entropy change, molar entropy change during fusion. That's why we have written this line. And then minus same thing, minus delta Gm fusion divided by T square. So ddt of ln activity of A is equal to this minus minus, both side minus. So therefore what happened? If we take minus common, so minus minus will get cancelled, plus, so here 1 by R, then delta Sm fusion divided by T plus delta Gm fusion divided by T square. We'll take T square as LCM, then we'll get this one. T square divided by T, that means T delta Sm fusion plus delta G molar. Molar gives free energy change during fusion. And here it is 1 by R, that is this term is equal to ddt of ln A, activity of A. So once again you have written this one. Now here, so ddt of activity ln activity of A is equal to, now look at here, this equation, we know that G is equal to H minus Ts. So therefore what can I write? H is equal to G plus Ts. Okay. So delta G plus T delta S. So therefore delta G plus T delta S, that will be is equal to what? Delta H. Okay. So here it is same thing. So this is molar enthalpy change during fusion, right? And this is known as the latent heat of fusion, okay, per mole of the solvent. So here this delta Hm, that is the molar enthalpy change, molar enthalpy change, enthalpy change during fusion, or latent heat of fusion, latent heat of fusion per mole of the solvent. Okay, so this is this one. So now this T we have taken this side. So d ln A, ln activity of A is equal to 1 by R delta Hm fusion dt by T square. Now integrating within the limit. Limit is A1. A1 means the activity of the pure solvent. Activity of the pure solvent is equal to mole fraction. So you can write it is equal to XA. And A2 activity of the solvent in the solution. Then is equal to delta Hm fusion by R. Then this limit is TF. That means the freezing point of the pure solvent to the freezing point of the solution. Okay, dt by T square. Now here activity of this pure solvent, activity of the pure solvent, as I told you, A means ln D, integration of D ln activity of A, that answer will be ln A. Ln A upper limit minus lower limit. Okay, upper limit is A2, but lower limit is activity of the pure solvent, which is equal to mole fraction. Mole fraction of the pure solvent will be equal to activity of the pure solvent is equal to XA. Pure solvent means this will be equal to 1. So A1, that is lower limit will be 1. So ln 1 will be 0. So it will be only ln A2, that will be equal to delta Hm fusion by R, and this integration I think you can do it. That means t to the power minus 2. Okay. So t to the power minus 2 plus 1 divided by minus 2 plus 1. So minus 1 by t, and limit is tf to t. So ln A2 is equal to delta Hm fusion by R minus 1 by t, limit is tf to t. Then ln A2 is equal to minus delta Hm fusion by R. Then we put the limit, okay, upper limit 1 by t minus lower limit. So ln A2 is equal to these things. Now here t into tf, okay, so it will be tf minus t, right? So ln A2 is equal to this part into delta tf. Tf minus t is delta tf, and here I have written tf square instead of ttf. Why? Since the solution is dilute, so this T almost is equal to TF. That means freezing point of the pure solvent is almost equal to the solution. So therefore what we have written, this TTF, that will be, I can write almost equal to TF square. So that only it is written here. Now ln activity of the solvent in the solution state, that will be mole fraction into activity coefficient, right? And then again right hand side it is the same thing. Then once again, as the solution is dilute, here activity coefficient of the solvent will be almost equal to 1. So since the solution is dilute, once again the same thing, then activity coefficient will be almost equal to 1. Okay, right? So activity coefficient 1 means it is log A into B, log A plus log B. So log A means ln XA plus log B will be 0. So this is equal to minus delta Hm fusion, latent heat of fusion per mole, divided by RTF square into delta TF. Delta TF is the depression of freezing point. So once again the same line we have written. Now in place of XA we can write 1 minus XB. XB is the mole fraction of the solute, and there are only two components, one solvent, one solute. So XB is the mole fraction of solute. Okay. So we can write and mole fraction of the solute, and we can know that XA plus xb is equal to 1. So 1 minus xb you can write, right hand side same thing. So if we expand and if we neglect the higher term, the answer will be minus xb, that is equal to this minus latent heat of fusion per mole divided by RTF square into delta TF. Now in place of xp, that is mole fraction of the solute, I can write number of moles of solute divided by number of moles of solvent plus number of moles of solute. Now next line, I can approximate it as in place of Na plus Nb, I can write Na. Here once again, since solution is dilute, since solution is dilute, then your Na must be much greater than Nb. So Na plus Nb, I can write almost equal to Na. So that only you have written here. So delta TF is equal to this Nb, okay, this one, if you take cross multiplication, Nb RTF square divided by delta HM fusion into Na. Okay. So this delta TF, what we have written there, same thing I have written. Now, so delta TF, in place of number of moles of the solute, we can write weight of the solute divided by molecular weight of the solute, MB. This is wrong. WB by MB. So here, number of moles of the solute, we can write it as WB by weight of the solute by molecular weight of the solute. Okay. So this is the expression. So from this expression, if we can determine depression of freezing point, we can calculate this molecular weight of the solute. Okay. Now see, let us consider weight of the solvent is Wa. So Wa gram of the solvent contains Nb moles of the solute. So 1000 gram of the solvent contains Nb by Wa into 1000 moles of the solute. That is the molality. That is number of moles of the solute present in 1 kg or 1000 gram of the solvent. So that is molality. Molality of the solution is Nb into 1000 divided by Wa. So from here Nb will be is equal to M into Wa divided by 1000. So once again I have written this equation, and in place of Nb is molality into weight of the solvent divided by 1000. In place of Nb we have put the molality weight of the solvent divided by 1000, then remaining as it is RTF square delta HM fusion into Na. Okay. Now next line, here in place of number of moles of the solvent we can write weight of the solvent divided by molecular weight of the solvent. So Wa by Ma. Now this Wa and this Wa getting cancelled. So delta TF will be equal to M RTF square 1000, then delta HM latent heat of fusion per mole divided by Ma. So this thing will be is equal to latent heat of fusion per gram of the solvent. So this one delta HM fusion divided by molecular weight of the solvent, that is the latent heat of fusion per gram of the solvent, and that is equal to say LF, small LF. Okay. So here, so these things M RTF square 1000 in this place, then what can I write? I can write this is, here it is LF. So from here we can write delta TF, this we make it in a square bracket. So from this one more line will come, that is delta TF, that will be is equal to MR TF square divided by 1000 into LF. Okay. Now you see this R constant, TF, that is the freezing point of the pure solvent constant, 1000 constant, LF, latent heat of fusion per gram of the solvent constant. So this whole term is constant. This whole term is constant. So delta TF, this constant. So this delta TF, we can write some constant KF into molality. So these things here I can write it as, this is molality, or here I'll write this is some constant which is known as the molar depression constant into M. Okay. So delta TF is KF molar depression constant into M. That means depression of freezing point directly proportional to the molality of the solution. Okay. Now, how can you define this constant KF molar depression constant? Look at here from this equation. When molality M is equal to 1, then this KF molar depression constant is equal to the depression of freezing point. Then Kf is equal to delta Tf. So, molar depression constant is the depression of freezing point when molality of the solution is 1. Okay, that is the definition of molar depression constant. Hope you have understood. Thank you.